Yes, is this okay like this?
Yeah, perfect.
Okay, thanks for the introduction and inviting me here. It's great it was already a very interesting session, so I learned a lot. Well, maybe first a disclaimer. So I will discuss a little bit about how I have done this, but this is not necessarily the way to go. And also, I didn't review any instruction documents or anything like this. So I'm just repeating how I have it in my head, but it's not necessarily the way to go. So I will first. I will have a little bit of different approach than the previous speakers. I will go a little bit or try to go a little bit into technical stuff because I want to be able to explain whether I stick to the same topic or not. And for this, I need to have a minimal explanation. And I promise I will not make it a scientific explanation, but it will be very minimal so that you can at least follow this point. And so first of all, the main grant. And so the main grant was on a technique which is called chromatography. And so chromatography, you can see on these slides what you do there is this. So chromatography is the most important analytical separation technique that you have out there. And so that's typically when you are very ill, you go to the doctor and you will do a chromatographic analysis of your blood. And so what's happening there is you inject a sample volume, and then you will have interaction with the wall of a channel. And then the components that have more interaction with that wall, they will go slower, and this band will move and will be brought to a detector. Now, as you can see, these bands have become broader. If they would not have become broader, they would be narrower, and they would have more space to separate more of those sample bands. So basically, you can do more complex analysis, or you could do it also much faster because you would not need such a long column anymore. So that was the main problem. And how can you overcome that? And all this is limited by slow transport of molecules in channels. And how can you overcome that? By increasing that transport. And so this is normally a natural, slow, diffusive process. You cannot do anything about it. And this is being done in very small channels where you do not have turbulence. And so there are no ways to enhance this mixing. And so if you do this, so if you have vertical mixing, you can see that if you generate a flow perpendicular to the main flow dimension, and then you can see that this sample band that you see here, in the absence of this kind of flow, you see something like this. But if you would do mixing in these microchannels, then the bands remain narrow, and what I just explained a few slides ago will take place. And so the core of the project was actually about simply trying to make these vortex flows in micron channels. And so that was the main essence of it, and doing this with oscillating electrical fields and things like that. And then the application was chromatography, but we would have been already very happy, and we were already very happy that we could show a first chromatographic experiment towards the end of the project, but it was certainly not the intention to end up with an instrument that could do all these things. And so this is again to conclude on the main ERC topic. So if you have mixing, if you have vortices, as you can see in the right image, then these bands stay narrower and you can have a better separation. Now, when you make these vortices, one of the big first challenges was how can you visualize these three-dimensional flows? Because with a conventional microscope, you just have a 2D view and you don't have a 3D view. And so this was actually a very important technology that we needed to interpret if the system was doing what it had to do. And so we had to develop within the projects a system with which we could have this 3D imaging. This was, let's say, a reconfigured confocal microscope in which we have an oscillating chip into the system. And so that was, in first instance, serving the project proposal by itself, but I'm also engaged in a bunch of other activities. And so I knew very well that one of the big problems is fouling. In solids in microreactors, you have particles, and these particles, they clog the reactors. It's a general problem in microfluidics. And so to overcome problems for that, you need to understand very well how three-dimensional flows are going and so on. And so what we did with this with this proof of concept proposal is, first of all, we stated that we would build this instrument. This technology was not available. There were some techniques available, some very complex instruments available, but they could not do the real-time imaging that we needed, very fast imaging, high resolution that we needed as in the project here. And so instrument, but also more broadly, you could also it could also be a tool in design and conceive microfluidic devices that can, for example, where you would not have fouling and so on, but where you could also have new types of activities or principles. When we involved one company. We had one support letter of one company that had a genuine interest also to be involved, but no strong engagement. And we also had a filed patent on the technology. And so this is the first example, quite off topic of the real project. And so it's a technological development, an instrument that we built, but then we are trying to valorize the instrument by itself. Then the second topic is it's closer to the real project. So here, quite early in the project, we could show, or we knew that our concept would work, and so next to having a technique that works, if you really want to go towards a valorization trajectory, then you need to have an instrument, but you also need to reconfigure these channels to do very specific applications. And so if you do this, and then you can think of totally other ways of using this chromatographic device. And normally this is being done in an expert lab, a very bulky instrument. But here we had all key ingredients to make a point of care device of it, to miniaturize the system, and to do other types of separations in other settings. And so this required, the team is still the same as in the main project, but we had to develop here an instrument, and also, let's say, we had a quite targeted application for this. And so but let's say this was quite in line with the project. We again had a filed patent on this one, and so the core technology was protected, and we had again one company involved. Then the third example is this is about again a different application where the technology that we have developed here. Basically, we are developing mixers, and you can do this mixing in micron channels, but you can also do it in larger channels. And in these larger channels, then you come quickly to the field of flow sensors. And so many flow sensors, like in the area of water monitoring, for example, but in general, in biotech, there are a lot of sensors out there. And all these sensors, they rely on the fact that you need to bring molecules to a sensor surface, which goes slowly by diffusion or by a bad mixer. And you need to enhance that if you want to reduce your analysis time, or if you want to increase the volumes that you could analyze. And so basically, we were using now a mixing technology, but it's a different mixing technology than we had in the main grant. In the main grant, we had an electro-osmotic mixing technology. As a fallback scenario, we had an acoustic mixing scenario, and that's what's depicted in here. And we were also from the start working on that fallback scenario already. And it became very obvious that this fallback scenario by itself was a very powerful mixer. And so that's what we have used then in this sensor type of device. This is repeating what I just said orally. These red dots are molecules that you need to bring to the sensor surface. Many of them will never touch the sensor surface, so you have very limited detection sensitivity. If you would have a very fast mixing, as we were planning to do acoustically, then you will have a much more sensitive mixer, but also you can flow much faster. And so this opens a new generic technology for sensor applications. And so these are, I hope this was helpful. These were 3 more concrete examples. Showing a bit how they were positioned with respect to the main grant. Then I put down some main reflections. I must say that most of this has already been discussed in the excellent presentations earlier in this session. But I think, first of all, or that's at least how I always interpreted it. All the technological work, if there is technological work, should be different than what you have in the main grant, simply because you cannot have double funding. So that was always my view, and so I always did my best, and it was in reality also always like that. That it was not just an extension of the main grant. This has been said. Also, this is not a real fundamental science project, and I think quite some people have difficulties with this because we have the best researchers, often the best fundamental researchers in the ERC schemes, but they're often not so much busy with valorization, and so it's a bit out of their comfort zone to write more a valorization type of project, because this is what it is here in ERC POC project. Then in general, I think this is more a general advice that I would give. I think always, whatever statement you make, you should always try to convince the reviewers with some type of estimation or link to literature, but as detailed as possible. I always think it's not good enough just to say that I hope it will work or I'm convinced that it will work. No, you should really convince as much as you can. And I think that's also, if you're building an instrument, even that instrument, if there are things to be done, you need to go enough into practical and technological details to explain why that is the case. Okay, but then maybe more importantly, so these POC projects are intended towards concrete valorization. So you really, I have always foreseen business development work, money for a business developer to work on some of the questions we have with respect to the business. You should be, you need to use the language of business development type of projects. So you need to speak about TRLs, and you need to say very explicitly the technology readiness level. And you need to say, for example, you want to bring it from 1 to 4. I think you need to be explicit. You need to, that has been said, you need to think of the competition, what is out there, why is it not good enough, or maybe it's too expensive, or maybe it's not fast enough, or things like that. So you need to position yourself very well against them, and maybe you even need to do more business activities to figure out that better. Then IP position is of course important. Do you have a patent? Do you plan to have a patent? What do you plan to do? How do you plan to cope with that? Maybe you want to keep a trade secret or something like that. But I think you need to put these things down explicitly, and that's important. What kind of product will you make, or an instrument or a service? In one of the examples here, we are developing an instrument, but you could as well say that this instrument would serve to make a service, for example. So I think these are different approaches you can have with the same type of technology you have in your hand. Then you need to be concrete on the impact that you will have, and you can say that in a generic sense, like in my example of the sensors, that you can improve the general concept of sensors, but you can also be very specific and say that you will make something for water analysis, for example. So I think that's important. And then what kind of valorization will you do? Do you want to go for a spin-off, or will you go for a license? It has been said, but I think it's important that you already mention in your proposal what your thoughts are and what your ideas are, and these can of course change, but it's important that you are considering this in advance of submitting the proposal. And with this, I would like to thank ERC, of course, for all the funding, and you for your kind attention.